nanohub.org. So today's lecture is a follow-up on what we were discussing in the previous lecture. I had to cut that lecture short, so this is going to be just about 10 minutes on an introduction to contact mechanics. Try to give you some background on these contact mechanic models that we will study in more detail as the course progresses. Okay, so the purpose of today's lecture is to provide a brief introduction to contact mechanics. And this is a subject that we'll come back and discuss in greater detail in future lectures, but we thought it would be a good idea to just introduce the words and the main ideas that have been developed to describe how a tip comes into contact with the substrate. So there's really two views that you can take on this matter. One is an atom-atom view, in which you view the tip as a collection of a few atoms that interacts with a few atoms in the substrate. That's shown on the left-hand side of this slide. This is perhaps the view that physicists or quantum chemists might take. The other view is more of an engineering approach, where you would say, well, the tip is comprised of a few hundred atoms, substrate is comprised of a few hundred atoms, and so maybe the interaction or the contact between the tip and the substrate can be described by continuum elasticity models. These continuum elasticity models have been developed in the literature for well over 100 years, so there's a large number of these models to consider. We're going to focus on 3 in this particular lecture, but there will be about a half a dozen different models that will be introduced throughout the remainder of the course. Right? What do we want to know when we talk about contact mechanics? What exactly would we want to know? Well, we like to know the nature of the contact. We like to know whether the contact between the tip and the substrate is reversible or whether it's hysteretic. We like to know what the contact radius is. So when the tip comes into contact with the flat substrate, exactly what is the radius or what is the contact area that's involved. And we like to know that as a function of, let's say, the applied force. We like to know if there's any deformation between the tip and the substrate, and we like a quantitative number for that deformation. We'd also like to know if there are any adhesive forces, if the tip sticks to the substrate, so that if we pull the tip away from the substrate, how much force is required to remove the tip from the substrate. And then lastly, we'd like to have some analytical models that describe all of these properties in terms of formulas that we might be able to use. So these are the sorts of quantities that we like to worry about, right? The continuum description of contact has a long history, right? It goes all the way back to 1881, when Hertz considered contact of a sphere with a flat surface. Hertz's model was really the first model of this contact mechanics, and of course it didn't worry about any of the surface forces that we discussed in the previous few lectures. So van der Waals forces weren't really appreciated in 1881, and so Hertz just assumed that you had a rigid sphere interacting with a rigid substrate, and he analyzed that situation, and his formulas for contact are probably the easiest and the simplest ones to understand. There have been other attempts. We'll talk a little bit about Bradley in 1932. Bradley considered 2 rigid spheres interacting solely by 612 atom-atom interactions. So again, he neglects all these long-range van der Waals forces that we discussed previously. And he just considers the contact of atoms according to this 612 Leonard-Jones potential. The 1970s saw a large number of a lot of activity in this area, and in particular, there are 2 models that have emerged from the 1970s. One is the DMT model. DMT model considers an elastic sphere interacting with a rigid surface, but now it includes these van der Waals, these long-range van der Waals forces. So molecules or atoms in the tip interact with molecules or atoms in the substrate, even when they're not in contact because of these van der Waals forces. And these additional van der Waals forces can change the nature of the contact. So the DMT model considers that. A remarkable paper from the early 1970s, the JKR model, published in 1971, is really clever. If you read the original paper, it's a really clever exposition of contact of a soft tip with a soft substrate. So they're particularly concerned about soft materials, and they also include short-range interactions, and they find a very hysteretic contact. So the contact that's formed on approach and the contact that's formed as you remove the tip from the substrate now becomes very hysteretic, in contrast to the DMT and the Hertz and the Bradley model. And then finally, in 1992, Moji published this theory, which is even more accurate. It's actually a combination of JKR and DMT, and it allows you to bridge the gap between the JKR theory, which is applicable for soft substrates, and the DMT model, which is more applicable to harder substrates. Moji's theory, we'll discuss briefly, allows you to go smoothly between those two limits. This slide is an attempt to remind you of this Deryagan approximation that we discussed about 2 lectures ago. And this Deryagan approximation is interesting because it allows you to infer the interaction energy between 2 planes. That's this quantity U that's marked in red in this slide. It allows you to infer that quantity based on the adhesion force between the tip and the sample. All right, so this is it's almost like a numerical consequence of considering van der Waals forces between objects. The quantity in red, the U of R, or the work that's required to produce a surface, which is labeled by W132 in this slide, that's a fundamental quantity. Tells how atoms of one substance interact with atoms of another substance per unit area, right? Per unit area. So it assumes flat planes interacting one with another. The terms on the left side of this equation, the force of the tip sample or the adhesion force, is something that you might be able to measure with an AFM. And so there's a connection between something you can measure and something that's of fundamental interest, okay? And this is kind of the connection that we're trying to make in this discussion. We're trying to get information about fundamental properties by measuring real tips interacting with real substrates. The problem is, right, the big problem is that real tips and samples are not rigid, and that was the approximation that Deryagan made. And so we have to use these other models, these Hertz, the DMT, the JKR, the Moji model. We have to use those models to better describe what's going on. But that sort of provides a motivation for what we're trying to talk about in this short lecture. I have to say a quick word about notation, right? When we discuss these surface energy problems about 2 lectures ago, we only considered 2 surfaces interacting one with respect to another in a vacuum. So in that situation, we were talking about the work W11 to create 2 surfaces of a material. So if you take like a piece of gold and you break it in half, what is the energy required to break it in half, right? In that case, you got gold and gold. Right? And so you get this parameter gamma sub 1. We generalize that discussion to the interface between 2 dissimilar materials. So for instance, if you have gold and silver and you have them put together and you break them apart, ideally what energy is required to break them apart? When you break them apart, you got 2 different surfaces now, surface 1, surface 2, and you've got this interaction energy gamma 1, 2. Okay, that has to be introduced to take into account the fact that the surfaces are dissimilar. We're now going to generalize that discussion even further. We're going to talk about 3 different materials. So we're going to talk about material 1 in contact with material 2, and those 2 materials are now surrounded by a 3rd medium that we call 3. And so we're going to say that the work required to separate surface 1 from 2 is now represented by this term W132, right? Where 132 is the surface energy of material 1 with respect to material 3. Gamma 23 is the surface energy of material 2 with respect to material 3. And then gamma 12 is that interfacial energy that was there when 1 and 2 were in contact with each other. So the material 3 can be imagined to be a liquid, right? So water or methanol, or it could be air or vacuum. If it's air or vacuum, then the discussion falls back to a simpler notation. But you'll find it in the JKR model, this parameter W132 is introduced, and it's just a generalization of these cohesion energies and adhesion energies that we discussed earlier. Okay. The other thing we need to know something about is we need to know something about the stiffness of the tip and the substrate. And so I wanted to just put a slide in to raise awareness of what we mean when we talk about stiffness of these materials. In particular, we're talking about the Young's modulus of the materials that make up the tip and make up the substrate. The Young's modulus is a modulus of elasticity. It describes how the material deforms under certain strains and stresses. And it's a number, and the number is measured in pascals or newtons per meter squared. So it's a force per unit area. The thing I want to remind you of is that this Young's modulus can have a wide variety of different numerical values. In fact, there's depending on which material you're studying, there's about 5 orders of magnitude variation of the Young's modulus. And this chart does not include biological materials, which are even softer yet than the foams and the rubbers. Okay. So way at the top there where you see ceramics, 1,000 gigapascal Young's modulus, that's probably characteristic of diamond, right? One of the hardest materials known. And then depending on what class of material you're looking at, metals, alloys, wood products, polymers, foams and rubbers, right? The Young's modulus can vary downward by about 5 orders of magnitude. So it becomes important to have numbers associated with the Young's modulus. For instance, for the tip, which tends to be made out of silicon, for whatever substrate you're looking at. And depending on what material system you're involved with, right, you got to know roughly where the Young's modulus is, because that's going to be an important parameter in the Hertz, the DMT, the JKR, and the Moji model, right? So just wanted to try to warn you in advance that you need to know those numbers. So in particular for your term projects, right, this is an important consideration. You have to have a sense of what the modulus is of your substrate. This slide just is an attempt to summarize the standard results that obtain for the Hertz, the DMT, and the JKR model, right? And I quantify, or I give the standard formulas that you would find if you read those papers in detail. The first panel shows the model of the tip, a spherical tip interacting with a flat substrate. And the first panel on the right shows the contact radius that you would expect if you push the tip, which we model as a sphere. If we push that sphere into a flat substrate with a force F, right? So the force F is given in newtons. If you know the radius of the tip, and if you know the total elastic modulus of your tip substrate system, now the total elastic modulus is defined in this panel at the bottom right of the slide, right? You have to know the modulus of the substrate, that's E sub S. You have to know the modulus of the tip, that's E sub T, right? You also have to know the Poisson ratio for the substrate and the tip. The Poisson ratios are given by this variable nu sub S and nu sub T. So to a very good approximation, if you have a reasonably isotropic solid, nu is about 1/3 for most solids. That's usually the approximation that's made. And in order to solve any of these expressions for, let's say, contact radius or deformation, you got to know what the effective modulus is of your tip substrate interaction, and you have to calculate that using this formula that I've got drawn in the bottom right slide. Very often you'll find different literature, right? See that factor of 3 force out in front, sometimes that's included in E total, sometimes it's not. Sometimes they define a parameter called E star, where E star is marked in red, and then E star is just the quantity in parentheses, okay? So sometimes you'll find that E total is written as 4/3 E star, and sometimes you'll find this longer expression. You shouldn't get confused about that. But the point is the contact radius for the 3 different models is a function of the force applied to the tip is listed in that top panel. You can see that the Hertz model is particularly simple. All you need to know is the modulus of the tip substrate. You need to know the radius of the tip. You need to know the force that you apply. You can calculate the contact radius A. On the other hand, the JKR model, which involves a tip with a soft substrate, right? You have to know all kinds of parameters before you can even estimate the contact radius for JKR. And likewise, there's a similar expression for the deformation that occurs, deformation that results when you push the tip into the substrate. Clearly, that deformation is going to depend on how hard the substrate is, how hard the tip is, right? The softer the tip and the substrate might be, the more deformation you might expect, right? The harder they are, the smaller the deformation. But again, there are parameters, right, for Hertz, DMT, and JKR that tell you what the size of the deformation is as a function of the applied force. The parameter A in deformation implies that you have to go back to the top panel and pick out the right radius for the model that you're using, right? So A is always the contact radius, and you have to somehow sort that out depending on the model that you use. Lastly, we have each of these 3 models makes predictions about the pull-off force. So this is the adhesive force that the tip would experience after it comes into contact with the substrate, right? How much force does it take to pry the tip loose from the substrate? And depending on which model you choose to follow, you've got different expressions for these adhesive forces. None of these expressions includes contamination between the tip and the substrate, right? So you have to be very cautious if you want to infer this work of adhesion, this W132 parameter, right? That assumes that there's no water layers, there's no hydrocarbon contamination between the tip and the substrate. Those conditions are usually difficult to achieve experimentally. Yes, question?
So is the DMT and the JKR take into account the adhesion or cohesion forces?
Yeah, both the DMT and the JKR actually take into account van der Waals forces between atoms in the tip and atoms in the substrate.
And then the Hertz doesn't?
Hertz doesn't. Hertz is 1881. The Hertz model was developed in 1881. They didn't even know about atoms in those days, right? Much less van der Waals forces. So he had no reason to put those forces in.
And then if people use Hertz model to model, is that?
Yeah, so the question is, people use the Hertz model, and is that reasonable to use? Well, what I've learned is that people use whatever model fits their data, right? Whether or not the model makes any sense or not, right? That seems to be a common feature of all experimental work. We will talk at the end of this lecture about the regimes that are most appropriate for these different models. Right? There's a very nice summary slide that I'll show, which gives you a sense of which model is correct. Okay? So stay tuned. Just wanted to work through an example real quick to give you a sense of the values that you typically put in when you use these models, right? So I did the Hertz contact because it's simple and it's reasonably straightforward. I think I can work out the arithmetic on that. So if I make a mistake, please tell me next lecture. But I assume that the tip radius is 30 nanometers. I assume that we're applying a 1 nanonewton force, which is certainly within reason for AFM considerations. So if the tip radius is 30 nanometers, the tip diameter is going to be 60. I just assumed that we had 200 gigapascal tip, 200 gigapascal substrate. I assumed that the Poisson ratios were 0.3. I calculate an effective elastic modulus for my system, which is given by this equation for E total. I solve and I get E total at about 146 gigapascals. Using that number, the radius of the tip, and the force of 1 nanonewton applied, I estimate that the Hertz radius would be something on the order of 0.6 nanometers. So 6 angstroms would be the contact between the tip and the substrate, contact radius between the tip and the substrate, right? The deformation between the tip and the substrate, again, I just used the standard formulas from the previous slides. I get about 12 picometers distortion. So the tip and the substrate are so hard that when they push against one another, the deformation that occurs is really small, 12 picometers. By definition, pull-off force in the Hertz model is 0, so there's no pull-off force. And I just wanted to make a suggestion that the contact pressure, right? So you say to yourself, well, 1 nanonewton, that's pretty small, right? That's 1 nanonewton, but it's applied over a radius of about 0.6 nanometers, 6 angstroms. So if you calculate the actual contact pressure of between the tip and the substrate over that 6 angstrom contact radius, right, you get a contact pressure that's about 0.9 gigapascal, which is on the order of about 9,000 atmospheres. So if the tip exerts a 1 nanonewton force on a hard substrate, and if this Hertz model is even remotely accurate, right, the pressures that the atoms in the tip and the atoms in the substrate feel are really rather large. They're thousands of atmospheres compared to, the world that we live in. So most of us aren't familiar about thinking what happens when materials are subjected to those high pressures, even for a short period of time, right? But the pressures can be really high. Okay, and I just wanted to make that case. Okay. Right? I wanted to plot out the force between the tip and the sample as a function of the separation D between the tip and the sample for the 3 models, just to give you a sense of what the force looks like as a function of D. This will be particularly relevant for the next lecture, in which we will talk about how you infer D in an atomic force microscope experiment. So D is this very nice definition that tells us the surface-to-surface separation between the bottom of the tip and the substrate. And it's very easy to draw on a PowerPoint slide, but it's extremely difficult to measure accurately in an AFM experiment, right? But nonetheless, if you could measure D accurately, right, according to the Hertz model, the force between the tip and the sample as a function of D would be 0 until the tip makes contact with the substrate. And then once the tip is in contact with the substrate, the force applied would go as 4/3 to the E star power, right? Where E star was defined on the previous slide. Square root of the tip radius times this distance D to the -3/2 power, right? Or D to the 3/2 power. So, in the Hertz model, no tip substrate forces until the tip is in contact with the substrate. That's the characteristic feature of Hertz, okay? And if you think you have very hard substrates and very hard tips, then maybe Hertz model is appropriate for your situation. Next one I plot out is the DMT model. Now, DMT, right, the tip atoms interact with the substrate atoms even when they're not in contact, right? So these van der Waals forces are coming in. And so because there's van der Waals forces, right, you're going to get the van der Waals forces of a sphere interacting with a flat plane. And we showed about 2 lectures ago that van der Waals force is the radius of the tip r times this Hamacher constant h, which is a number on the order of 10 to the minus 19 joules. 6 is a number that comes out from all the integrations, and it's a 1 over d squared force, right? It's a 1 over d squared force. So even though the interaction energies are 1 over d to the 6, when you integrate that interaction energy over a sphere in a flat plane, you get this 1 over d squared behavior. And so as a result, when the tip approaches the substrate, if we could measure d very accurately, right, we would find that the tip experiences a negative force originally. The negative force means that the tip is pulled down toward the substrate, right? Tip is then pulled down, according to the Hamacher, or according to a van der Waals force, until it gets within this distance A0. A0 is a number that's basically the interatomic spacing between atoms, right? So it's a number on the order of 2 to 3 angstroms. Right? And then after that, there would be a repulsive force that would continue to increase as the separation D is decreased even further, right? And that the way the interaction force increases is very similar to what we saw in the Hertz model. It goes up as the 3/2 power of the separation between the tip and the substrate. And it has this characteristic behavior that I've got plotted here. So this is the second model that you'll find used to discuss tip substrate forces in the literature, right? The JKR model is even more complicated, right? It's hysteretic because the JKR model is most appropriate for soft substrates, hard tip, soft substrates. So there's about 3 different colors of lines on that graph, right? The best way to illustrate it is just to animate it very quickly. So if you just follow that black dot, you'll see what happens as the tip approaches the substrate. So as the tip sample separation gets small, you'll see what happens as you approach, and then you'll also see what happens as you withdraw. So if I click this button, something should happen, right? Right. So if you followed that, you would see that the red line describes the behavior of the tip as it moves into contact with the substrate. So there's no interaction force in the JKR model until the separation between the tip and the substrate is 0. Once the tip sample separation is 0, then there's a large attractive force that the tip is pulled toward the substrate, and as the tip continues to be pushed into the substrate, right, the tip sample's force increases. When you withdraw, right, the withdrawal curve is described by the green line. And there's a hysteretic behavior, and the green line shows that the tip actually sticks to the substrate until it finally jumps from contact. Okay? So the model is a lot more complicated. It involves a lot more parameters. There's an implicit relationship between the contact radius A and the separation D, right? And that implicit relationship that's shown on the 3rd line of this slide, that has to then be plugged into the first line on this slide if you want to actually calculate the tip sample force as a function of D. So this is a lot more complicated. I guess the other point I'll make is there's there's this work of adhesion, right, that's related to the area enclosed by that hysteretic curve. And that work of adhesion is often very interesting to different disciplines, chemistry or chemical engineering, right? And so, in principle, if you have a system that's described by the JKR model, you integrate the area under that hysteretic approach versus retract curve, you can get a parameter that's of fundamental interest, okay? So we'll talk more about all these models as the course progresses. I just wanted to say something about Maugy's model, because Maugy came up with this idea that the JKR and the DMT were just two limits of a continuum mechanics, contact mechanics theory, right? And so he developed in another remarkable paper, I think it was in 1991, he invented this parameter lambda, which I define on this slide. The details of lambda aren't terribly important, except that you have to appreciate that lambda is roughly proportional to the ratio of the adhesion to the elasticity of the tip sample contact. So W132, that's telling you something about how the tip adheres to the substrate. The parameter E total squared in the denominator, that's got something to do with the elasticity of the substrate. And so what you find is that this parameter lambda is small if the adhesion is small, and the parameter lambda is large if the adhesion is large, okay? And so, if you read Maugy's paper, right, he's got these very complicated graphs, which I try to simplify in this diagram, and these graphs are very useful for interpolating DMT model to the JKR model for different values of that parameter lambda. So I think if lambda is 0, or if lambda is a very small number, then you've got the DMT model that's appropriate. As lambda gets very large, as it approaches infinity, then you go to JKR, and for any value of lambda in between, you've got you have to follow the appropriate line for the appropriate value of lambda for your system, right? So in Maugy's model, he's got a detailed graph that shows how the contact radius varies as a function of penetration. The blue line on this curve shows you how the normalized penetration varies. As the normalized penetration varies, how the contact radius increases, right? So the blue line is for both Hertz or DMT. And then for the JKR model, it's a little bit more complicated, right? I try to show that here. So the basic idea is that you approach from the left side of this graph up until this normalized penetration parameter is equal to 0, the tip is approaching the substrate. When the tip comes into contact with the substrate in the JKR model, right, there's an abrupt jump, and the contact radius goes from 0 to some finite value. As you then increase the penetration by increasing the force between the tip and the substrate, right, the contact radius increases. And then as you withdraw, as you pull the tip away from the substrate, the JKR model predicts that the radius of contact will not go to 0 in a reversible way, right? There's actually hysteresis. There's actually a neck of material that forms between the tip and the substrate. And that neck requires a force to pull the tip away from the substrate. And you can see the neck will finally break, as the penetration now is a negative number. That basically means you've had to pull the tip back away from the substrate in order to release the tip from the substrate, right? So that red line that I superimposed on there is an attempt to show you what the JKR model predicts. And then depending on what lambda parameter you have, right, you can have any value in between those two, right? So as you go, as you make the substrate softer and softer, you go from the DMT towards the JKR model. And in the limit, when the material is really soft, then you have the full JKR model and you follow the red curves. There's also an equivalent plot in Maugy's article that describes the normalized loading force versus penetration, normalized penetration. And again, the Hertz, the DMT, and the JKR model are shown. The Hertz behavior is shown in blue. The DMT model is shown by the red line. And then the JKR model, which is very hysteretic. You get different behaviors approaching and retracting. That's also shown in green. So this gives you a sense of what these different models are saying, okay? And again, this will become, this will be discussed in more detail, especially in the next lecture where we actually start to talk about the tip substrate forces. Okay? So I think, this is an answer to the question that was asked earlier about which regime is most appropriate for which model. Okay? So again, this is a complicated graph, but it shows how the different models interlay one with respect to another with regard to this parameter lambda. And again, this parameter lambda is roughly a measure of the ratio of adhesion to elasticity, right? So that's plotted on the x-axis. Along the y-axis, we're basically plotting a normalized parameter that's roughly equivalent to the ratio of applied force, F, divided by the work of adhesion, W, okay? Now, things are scaled by the tip radius, as you can see, but if you have a constant tip radius, that's probably the easiest way to think about this diagram. So, for instance, if you have a very hard substrate with very little work of adhesion, then your normalized forces are going to be down around 10 to the minus 1 or 1 on this diagram. And you can see that if the adhesion is very small, which means lambda is a small number, so we're in the left-hand side of this diagram, then Bradley's model is pretty good, right? Bradley's model, which just describes the contact between atoms using the Leonard-Jones potential, is pretty good. And as you continue to increase either the hardness of the sample, as you continue to increase the adhesion of the sample, so lambda gets bigger, you move from left to right, you see you go through this DMT regime, right? Then there's this intermediate regime MoG, which requires you to evaluate things in a very complicated way. And then finally, as the adhesion dominates, lambda is a big number, right? You're on the far right of this graph and the JKR model becomes appropriate, right? If the work of adhesion is very small, right? So if there's no adhesive properties between the tip and the substrate, then your normalized forces are very high, right? So you're in the upper part of this graph. You can see that the Hertz model is probably okay for all values of adhesion, of the ratio of adhesion to elasticity, right? So as you get to small enough adhesion, big enough values of this normalized force, then the Hertz model tends to work okay. And so for the experimentalist, it's important for you to decide for a given system, if you're doing force versus distance curves, for instance, it's important for you to decide roughly where you're at on this plot, because that's going to tell you which of these models is going to be most appropriate for your experimental situation, right? And of course, the difficulty is it's sometimes hard to know what W132 is. Right? That's a hard number to know from first principles. So you have to be able to estimate it. Usually you'll draw a circle on this graph, which accurately represents your confusion about the uncertainty in these various parameters, right? And then hopefully that circle will lie squarely in one of these regimes. Okay, so that's why this is a very useful plot to know about. Okay, shows how everything is interconnected. So, these are just a bunch of comments you can read and sort through on your own. I think as an experimentalist, I like to focus on that third bullet. All of the equations, JKR, Hertz, and DMT, have been tested experimentally, and they are actually very accurate if your surfaces are smooth, right? So, for instance, I know JKR has taken rubber balls, centimeters in diameter and pressed those balls between glass plates and looked with an optical telescope at the contact radius of the ball with respect to the plate, because you can measure it experimentally, right? And they can verify their model in terms of these very, very nice experiments. But it neglects all kinds of surface roughness issues that would apply when the tip is 30 nanometers in diameter, right? All the experiments tend to be done on balls that are centimeters in diameter. So there's an issue as the tip gets small and the substrate gets rough, right? How accurate these models really are and how they apply. That's part of the business, right? This fourth point here is that the most practical limitation for AFM is that no tip is a perfectly smooth sphere, right? That just you can't buy those. And small asperities on the tip will make a big difference. So you shouldn't be terribly surprised if these models don't work for AFM purposes, right? I think we're at the point now where we're ready for the next lecture. Next lecture is going to actually discuss how that tip interacts with the substrate, and the tip is now going to be attached to a cantilever, so we're going to have a force sensor, and Professor Rahman is going to go through the details of how the tip deflects and how the tip deflection can be used to infer the separation between the tip and the substrate in an experimentally meaningful way. So I think I'll stop here, and then we'll turn the floor over to Professor Rahman for the next lecture. So be happy to answer any questions at this point.
The simulation there says sample equals HOPG.
Say what?
On the figure, it says sample equals HOPG, the material.
Yeah, so what you have to do is you have to specify the tip material and you have to specify the substrate material. So what that notation is trying to tell you is that the tip is made of silicon, right? And the substrate is a material called highly oriented pyrolytic graphite. It's an extremely smooth substrate. So HOPG is a definition for highly oriented pyrolytic graphite. It's a material that you can cleave very simply to produce atomically flat substrate. So for that reason, it's useful, right? And it turns out Professor Rahman did a number of experiments in the 2002-2003 time frame where he looked at this silicon HOPG system, right? And he was able to model the tip surface interaction forces in terms of this DMT model, which is listed in the top part of the slide. So if you look on Physical Review B, year 2000, or in Ultramicroscopy 2003, you'll see some very nice experiments that were modeled by this tip substrate interaction that was the DMT model, right? So that's the only reason we refer to this slide here, is it gives you an example. If you know the model, if you know the contact mechanic model, then you can interpret data, right? Okay. So I think we have to make a choice, right? Do we come back on Thursday and listen to Rahman's lecture, which is about 60 minutes, or do I put it in now and we'll get through 25 minutes of it before we have to leave? I think this is a question that has no correct answer. It's kind of like what you prefer. Say what? You want to say, okay, so then I'm going to stop it at 11:45. Then what happens? Do we come back on Thursday to hear the rest of it? Okay. Fair enough. Yeah. So the question is, how do you make those tips, right? Well, in the early days, you couldn't buy them, right? So we were making them ourselves by gluing pieces of diamond onto, we used to take like paintbrush bristles. You know what a paintbrush is? We take those things. We glue a little diamond tip on them, and we glue a little mirror on the back, and we deflect, we shine the laser beam onto that mirror, right? In the early 1990s, a group out of Stanford showed that you could make these cantilevers and these tips using these microfabrication techniques that the microelectronics industry had developed. And so what you can do is you can start with, let's say, a silicon wafer. I believe the orientation of the silicon wafer is a 100 orientation. And by applying appropriate photoresist masks onto that wafer, and then by using preferential chemical etches, you can actually etch along certain directions in silicon with a very high etch rate. And those directions of silicon that can be etched along with a very high etch rate then are used to form a conical tip on the end of a very thin silicon platform, right? So the wafers come in two varieties. Actually, they come in, the cantilevers now come in at least three varieties, right? You can get silicon microcantilevers. I believe you can get silicon nitride microcantilevers. And there's a movement coming out to make cantilevers out of nanowires. So out of carbon nanotubes and nanowires. Right? So the community has developed a tremendous number of innovations to make these cantilevers. But the short answer to the question is most of the cantilevers are made in clean rooms using microfabrication techniques that have been developed to make small submicron size transistors in your computer circuits, right? There are certain clean rooms and certain vendors that seem to make cantilevers more reliably than others. They seem to have better control of the etching conditions and the preparation conditions. So the variability of cantilevers and the quality of cantilevers varies an awful lot depending on the fabrication facility that actually makes them. And I think every experimental group in the world has their favorite source of cantilevers, right? Because for whatever reason, over time, they've found cantilevers from other companies don't work as well, or they're not as reliable, or they're contaminated, or whatever. I'm not a fab guy, so I've never made a cantilever in a clean room in my life, so I don't know how to do it.